Hi everyone and welcome to MathSux. This video is going to help you pass Geometry Common Core Regents. So we're doing this one question at a time, going over part 2. Here is question number 25. On the set of axes below, triangle DOG is congruent to triangle CAT. Describe a sequence of transformations that maps DOG onto CAT. So this is our original triangle and we're mapping it onto this triangle. So notice right away that this triangle, if we were to fold this in half along the y-axis, it would kind of look like the mirror image of this triangle. So let's start by saying a reflection over the y-axis. So let's draw that out on our coordinate plane just so we have something to go with. So this can be like O prime. And you don't actually have to do this on your answer sheet. Visualize the answer, what step should come next. So we start out by having a reflection over the y-axis, and then now if you look, we just are translating this up a couple of units. So let's see how many units we have to go up. So, and then we're going to translate up 5 units. And that's our answer. Question 26. In right triangle MTH shown below, angle H is 90 degrees, HT is 8, HM is 5. Determine and state to the nearest tenth the volume of the three-dimensional solid formed by the rotating triangle MTH continuously around MH. So it's asking for the volume of this shape as if we were to rotate the whole triangle around MH, around here. So around this line here. So if we were to rotate this, it would end up making this three-dimensional shape. So this is like one of those visualization questions that you have to think about. We'd be making a circle with the base, and that would be creating a cone, right? So we're going to be finding the volume of the cone. So the volume of a cone is a formula, which is just pi r squared h over 3. So now we can just fill this in and calculate for the volume of our cone here. So we have pi times the radius is 8. We have 8 squared times the height, which is 5 over 3. So we could just plug this into our calculator. So we get 335.103, but remember they wanted this to the nearest tenth. So we're just going to write 335.1. And that's our answer. Question 27. Using a compass and straight edge, dilate triangle ABC by a scale factor of 2 centered at C. So for this, we're going to be using our compass and straight edge. So the first thing I'm going to want to do is look at what we're centered at. We're centered at point C, which is over here. So I'm just going to extend the line stemming from point C. So we're dilating by a scale factor of 2. So that means we're going to be doubling the length of A and C and B and C. And then C is going to remain the same because we're dilating about this point. And this is a part of our triangle, so we're just going to leave it there. So to double the length of each of these triangle sides, we're just going to measure out one side, BC, and then to double it, we're just going to take this same length and then double it and make a little mark. And now to double our other line, AC, we're just going to measure it out and then take that same length and then make a little mark. And now we just need to mark our spots and connect our dots. And that's our answer. So it was pretty simple to do. It was directed at point C. If the point was out here, it would have been done a little bit differently. But we're just, with that scale factor of 2, we know we're just going to be doubling the lengths that already exist. Question 28. A rock climbing wall at a local park has a right triangular section that slants towards the climber, as shown in the picture below. The height of the wall is 5 meters, and the slanted section begins 1.2 meters up the wall at an angle of 14 degrees. Determine and state to the nearest hundredth the number of meters in the length of the section of the wall that is slanted, the hypotenuse. So this picture is a little confusing to look at because it is a real world picture. So I'm just going to draw it down here. So what we have here is the right angle, and here is 14 degrees. And then they extend this section saying this is 1.2 meters this way. And then this whole thing is 5 meters. So what that means is we can find the value of the length of this section of the triangle, which is going to be 5 minus 1.2 meters, which is 3.8 meters. And we want to find the value of the hypotenuse, they said. So I'm just labeling that X. Because this is a right triangle, we could just use SOHCAHTOA. So in order to find the hypotenuse, we're going to be using this information here. So we're dealing with this angle, so we're dealing with the adjacent and the hypotenuse. So we would be using cosine. So we have, because it's cosine is equal to the adjacent over the hypotenuse. So we have cosine of 14 degrees is equal to the adjacent 3.8 over the hypotenuse, which we don't know, which we're trying to find. And then we just use a little algebra in our calculator to solve this. So keep in mind they want it to the nearest hundredth. So we have tenth, and then hundredths, just rounding this up, 3.916 becomes 3.92 meters. And that's our answer. Question 29. In the diagram below, a right triangle BAL, altitude AD is drawn to hypotenuse BDL. And the length of AD is 6. If the length of DL, so over here, is 4 times the length of BD, so let's label this BD is X, and then DL is 4 times the length of BD, so that's 4X. Determine and state the length of BD. So we want to find X. So whenever you see a triangle like this with an altitude drawn, we know we're going to be dealing with similar triangles that are in proportion. So let's draw out, there's 3 triangles happening here, and they're all similar to each other. So this first triangle, I'm just going to draw them all out. So this first triangle we have is ABD, which we know is X, and then it's 6. And then we have this other triangle on this side, ADL, where AD is the same here. So we know we have 6 over here and then 4X down here. And then the third triangle is just the entire triangle we see here. In order to find the value of X, what we're going to do is pick 2 of the triangles and put them in proportion, set up a proportion. So notice here, these 2 triangles are going to work for us because these have values we can work with. Okay, so how do we do this? How do we set up a proportion? So what we're going to want to do is flip and rotate each of these triangles so that they match each other, and we can more easily see how to set up the proportion. So notice here I put the right angle up top, and then to the right, this is the long side of this triangle. Let me actually draw it so it's a little bit longer. So this is our longer side. So here's the hypotenuse, and then here's our shorter side. So now we're gonna flip and rotate this other triangle right here. Do the same thing, making sure that it lines up. Where we have the right angle up here, this is angle D, and then we want our long side. So our long side, notice, aligns with 4x, and the points DL. So what's left here is point A, and we know that DA is 6. So now we can set up our proportion. We can more easily see that. So now we can set up our proportion. So we have short side x over our other short side of the other triangle, 6. And we're setting it equal to the longer side of the first triangle, which is 6, and over the other longer side of the other triangle, which is 4x. And now we could just cross multiply. Until finally we get our answer of x equals 3. And if you go back and look, they just wanted to know the length of BD, which is x, so we know that this is 3 and we're done with this problem. Question number 30. Trapezoid ABCD, where AB is parallel to CD, is shown below. Diagonals AC and DB intersect MN at E, and AD is congruent to AE. So we can see that this is an isosceles triangle, AED. If DAE, angle DAE, so over here, is 35 degrees, angle DCE is 25 degrees, and angle NEC is 30 degrees. Determine and state angle ABD. So we want to find angle ABD. So we're looking for this angle right here. So there's so many different ways to start with a kind of question that's like this. But I'm going to start off using this isosceles triangle right here. So we know that there's 180 degrees in a triangle. And we know that this isosceles triangle is 35 degrees already, and we know that both of these sides are going to have to be equal. So we're going to take 180 minus 35 and then divide that by 2, and we get 72.5. So if you notice here, we also have a vertical angle on this side, so we know this angle is also going to be 72.5 degrees. And we know that this entire thing is a line, this line DB. So if line DB is a line we have, this all has to add up to 180, this whole thing. So what we're going to do is add 72.5 plus 30, and then subtract what we get from 180. And this gives us 77.5. You notice here, these are also vertical angles, so we can fill this in. So this is 30 degrees, and then this is 77.5. So now, over here, notice we can find this angle. So we're just solving as many angles as we can in order to find our missing angle B here. So let's see, we have this little triangle here. We can find this angle out, adding 30 plus 25, and then subtracting 55. And we get, this is 125 degrees. And we know that this is a line, and this has to add to 180 degrees. So we can subtract 125 from 180, and this gives us 55 degrees over here. A lot of this is just triangles and vertical angles. So as long as you know that a triangle adds to 180 and vertical angles are equal, then you should be good here. So now we can find this other angle right here, because we have another triangle in here. So we have 77.5 plus 55, and then subtracting that from 180. And here we have 47.5. So the thing that they mentioned before is that AB is parallel to CD. So because these are parallel, that means this line here is a transversal. So when we have a transversal, we have alternate interior angles and all these other angle relationships that form. So if this is 47.5 degrees, that means that this also, based on transversals, is going to be 47.5 degrees. And that's our answer. So we actually ended up using, so I'll label everything we went over. So this was based on this was isosceles triangle, and then a bunch of these were vertical angles. So we have our answer. We can state it down here. Angle ABD is equal to 47.5 degrees. Question 31. In the diagram below of circle O, the measure of inscribed angle ABC, so this is our inscribed angle here, ABC, is 36 degrees and the length of OA is 4 inches. Determine and state to the nearest tenth of a square inch the area of the shaded sector. So we want to find this area right here. In order to do that, we're going to be using the area of a sector formula, which looks something like this. So you notice it looks very similar to the area of a circle, but we're kind of dividing by the number of degrees we're working with. So there's 360 degrees in a circle, we're going to be dividing by however many degrees are in here, which is also the value of arc AC, which we're going to need to find. So how do we find the value of arc AC? So we're given that this is an inscribed angle, and because of that, we can find out what this is. So there's a formula for finding the arc based on the inscribed angle. So let's write that out. So we have angle ABC is equal to 1/2 of arc AC. So this is for all inscribed angles. This is a theorem that you're gonna have to know. So we know that angle ABC, when there's an inscribed angle, it's gonna be half the value of arc AC. So we know that ABC is 36. So we know it's gonna be half of AC, which is just gonna be 72. So we know that arc AC, or X, is equal to 72 degrees. So now knowing that, we can go back over here and plug in the values into our area of sector formula. So we have pi r squared, so the radius r is 4, so we have 4 squared, and then times x degrees, which we now know is 72, divided by 360. And now all we need to do is plug this into our calculator. So we have 72 divided by 360 times 16 times pi, and we get 10.053, and it keeps going, and we want it to the nearest tenth, our answer. So we're just gonna go round this first decimal place here is our tenth, so we're gonna round up because it's next to a 5, and we have our answer 10.1. Question 32. As modeled in the diagram below, a building has a height of 50 meters. The angle of depression from the top of the building to the top of the tree is T at 13.3 degrees. The angle of depression from the top of the building to the bottom of the tree is 22.2 degrees. Determine and state the nearest meter, the height of the tree. So we're looking for this height right here, this height of the tree. I'm just going to label it H. Also notice we can find the height of this whole thing here. This side is just going to be 50 meters. Just copying it over from this side. So we know we have triangles here, and we know we're going to be doing some trigonometry, some SOHCAHTOA. So just keep that in mind. there's different ways to go about this. So what I'm going to show you isn't like the only way to do this. So if you started another way, like keep going with that, see how if we end up with the same answer. So now I'll show you the way I solved it. This first thing I'm going to notice is that this forms a right angle. So this whole corner adds up to 90 degrees. Each of these corners are 90 degrees. And I know that because this is a building and it's flat, so we know we're dealing with 90-degree angles. So now, if we know that this whole thing is 90 degrees and we have this portion is 22.2 degrees, we know that we can just subtract 90 minus 22.2 to get the remaining value right here. So let's just plug that in our calculator. And we get 67.8. So 67.8 degrees here, and then this is 50 meters. And then now we can actually find the value of one of these long sides here using SOHCAHTOA. So if we're looking at, so I'm just going to redraw the triangle down here, the one we're focusing on. So this is 50 meters. This is 67.8 degrees. And then we want to find this value. Let's call it x. So to do that, we're going to have to use SOHCAHTOA. And notice what values we have here. So in relation to this angle, we have the adjacent and we have the opposite, or we're looking for the opposite. So if we're dealing with the adjacent and the opposite, we're going to be using tan. So we have tan of 67.8 degrees, and it's equal to the opposite, which is x, which we need to find, over the adjacent, which we know is 50. So just plugging in 50 times tan of 67.8 based on cross multiplying, and let's see what we get. So we end up getting this long number, 122.5212599. So I don't like to round until the end of the question because that can throw off our answer. So that's why I'm writing out the whole decimal. So now let's just fill it in. So we found x, and it's equal to what we just found, 122.5212599. So we have it on this value down here, but we know that's going to reflect up here as well. This will also be the value of 122.5212599. So we're almost there. So this was like the first big part of our question. Now for the next part, we're going to be looking up here at this triangle. So I'm going to bring it down. And I'm just going to call this height y. So we know that this up here is 122.5212599. We don't know what this is yet, but we want to find this value because we have this 50 here, and if we can subtract 50 from this value, we'll end up with our answer, the height of the tree. And let's see what angle we have in this triangle. It's 13.3 degrees. So if we're looking in relation to this angle, we have, this is the adjacent, and we want to find the opposite. So again, we have the opposite and the adjacent, so we know we're going to be working with tan. So we have tan of 13.3 degrees is equal to the opposite, y, over the adjacent, which we just found. So now let's find y. We just cross multiplying here. So we need to plug in 122, that big long number we found, and multiply it times tan of 13.3 degrees. And when we do that, we get another long number, 28.96279.854. So this represents y, this length right here. So notice what we can do now. We have this value 50 meters, which they gave us, minus, we could subtract that number we just got, 28 point. And whatever we end up with will be the value of h. So when we do that, we'll see that we get 21.0372046. And now we can round and start writing all these long decimals. So what did they want it to? The nearest meter. So the nearest whole number, which will just be 21 meters. And that's our answer. Question 33. The coordinates of the vertices quadrilateral hype are h, y, p, and e. Prove hype is a rectangle. The first thing I'm going to want to do is draw this out. So let's see, h is -3.6. So we need to prove that hype is a rectangle. So the way that we're going to do that is we're going to need to show that each of these corners is a 90-degree angle. And how do we show that there is 90-degree angle? So what we're going to do is find the slopes of each line and then show that they are negative reciprocals of each other and that they are perpendicular, which forms 90-degree angle. So that's what we're going to be doing with this question, writing statements and reasonings along the way and solving. So we're going to find the slope of each side of our rectangle, what we assume is our rectangle for now. So let's start with this side, this slope right here, hy. So I'm just going to write down the coordinates over here of h and y. And remember, to find the slope, we're always doing the change of y over the change in x. So I'm just going to put it up here. The slope formula is y2 minus y1 over x2 minus x1. So now we can find the slope. So we're going to subtract our y's, 9 minus 6 over our x, 2 minus -3, which will just give us 2 plus 3. And this will give us 3 over 5, or 3/5. Okay, so we found each y. So I wonder if this slope matches this slope down here. So let's try that line next. Line that forms with coordinates EP, where E is 3, -4, and P is 8, -1. Our slope is going to be -1 minus -4, so double negatives, we're going to have a positive, and then 8 minus 3. This will give us 3/5. So these two slopes match. So already this is looking pretty good. So let's now try these side lengths going down this way, the longer sides of this rectangle. So let's look at HE first. And we want to make sure that our slope is going to be a negative reciprocal of these slopes. So we can reduce this and get -5/3. So is that the negative reciprocal 3/5? Yeah, because we have 3/5, and then we flip the numbers and negate them. So 3/5 becomes -5/3. So we know that this is going to be a rectangle. So let's doubly check with our last long side length here, YP. And we get -5/3 again. So we know that these are negative reciprocals of these other slopes we found here. So now, unfortunately, we're not just like done even though we proved this true. You're going to have to write a formal statements and reasonings. So let's start that. So there's going to be a bit of stuff to write. So the first thing you always want to list in your statements is what we're given, and in this case we're given that height is a quadrilateral. And the reasoning for this is that it's given. So up next we're just going to list our slopes. So we're going to say that the slope of line HY and line EP is equal to 3/5. And our other slopes of HE and YP is equal to -5/3. And we found this just based on the slope formula. So next we can say that HY, we can start saying when things are perpendicular to each other. All these lines are perpendicular to each other, right? So we know that HY is perpendicular to HE. We also know HY is perpendicular to YP. And then we can go down here and say the same thing. So we know that EP is perpendicular to HE. And EP is also perpendicular to PY, or YP. And we know this because the slopes of perpendicular lines are negative reciprocals of each other. Okay, we're almost done. So now we're just going to mention that all these angles are right angles. So angle H, angle Y, angle P, and angle E are right angles. And we know this because perpendicular lines form right angles. And last but not least, we have our final statement and our final reasoning. We're going to say that height is a rectangle. And our reasoning is that a rectangle has 4 right angles. And that's our answer. So yeah, this one is there's a lot of writing in this, but the ideas and the concepts behind it aren't too hard. It's just more annoying than anything. As long as you know that a rectangle has 4 right angles, and we can prove that by using the negative reciprocals of slope, then you should be good. It just takes quite a while to write this all out. Question 34. A packing box for baseballs in the shape of a rectangular prism with dimensions of 2 feet by 1 foot by 18 inches, so be careful already. We have feet, and then in inches. Each baseball has a diameter of 2.94 inches. Determine and state the maximum number of baseballs that can be packed in the box if they are stacked in layers and each layer contains an equal number of baseballs. So first, let's draw out our rectangular prism, which is just like a 3D rectangle. And then it gives us these dimensions. So I'm going to convert all of them into inches. So 2 feet, let's say this is, the length is 2 feet, but this is also really 24 inches because there are 12 feet in a foot. I'll say that this is 1 foot, even though it's really 12 inches. And then right here, we'll say that the width is 18 inches. So we have that. It also tells us that the diameter of each baseball is 2.94 inches. So I'm just going to draw a baseball, a circle down here to represent our baseball. And we can see that the diameter is equal to 2.94 inches. So now we all have matching units, inches, inches, inches. Okay, so now let's take a look at this first part of our question again. Determine and state the maximum number of baseballs that can be packed in the box. So how many baseballs can we fit in here if they are stacked in layers, and each layer contains an equal number of baseballs. So I'm gonna just draw a little top bird's eye view of our box. So going this way we have 24 inches, and this way we have 18 inches. So if we know that the diameter of each baseball is 2.94 inches, how many can we fit along this way, just along this way? So what we're going to do to find that is take 24 and divide it by 2.94. So that represents the diameter. So going along this way, we'll be able to see how many you can stack along here. And we get 8. We get numbers after that, but we can't have like 0.16 of a baseball fitting in here. So we know that we have 8 baseballs going along this way. So we got that. And how about going the way where it's 18 inches, where the box is 18 inches long? So we're going to do the same thing, just divide by the diameter length. And here we get 6. And then we could just do this all the way down. So when we see that how many baseballs can we fit in here, we get 8 times 6, which is 48. But hold on, this isn't just our box, right? This is the bird's eye view. We actually have, don't forget our box is 3D. And we can actually stack them, like they said. We can stack them in layers. So remember that going down this way is another 12 inches. So we're gonna just do the same thing, 12 inches. How many baseballs can we fit in our layers that are stacked on top of each other? So we'll just divide by the length of the diameter and get 4. So now we're going to take our 48 and multiply times 4. And this gives us an answer of 192 baseballs. That means going up and down we can have 4 layers going all the way across. And that's why we end up multiplying all these numbers together, 8 times 6 times 4, and you get 192. Now let's look at the second part to our question. We'll just call it part B. The weight of a baseball is approximately 0.025 pounds per cubic inch. Determine and state to the nearest pound the total weight of all the baseballs in the fully packed box. So here we're going to multiply a couple numbers together. We're going to be multiplying the number of baseballs in the box itself, which is 192, which we just found. We're going to multiply the weight that they gave us per cubic inch, the weight. And then we're also going to multiply the volume of the sphere of the baseball itself, which is 4/3 pi r cubed. So notice they don't give us the radius, but they did give us the diameter, 2.94, and the diameter is always, given the diameter, you could always find the radius and just divide by 2. So we get, this is 4/3 pi r cubed, and this represents the volume of the baseball. This represents the weight of the baseball, and then this is the number of baseballs. So all we have to do now is plug this into our calculator and see what we get. And we get about 63.86778445. So when we look back, that's not going to be our final answer, right? That's way too long. But if we look back at our question, they want it to the nearest pound. So the nearest pound is just going to be 64 pounds. So we're going to round up. And that's our answer. Question 35, our last question. Given quadrilateral ABCD, AC and EF intersect at H. EF is parallel to AD, EF is parallel to BC, and AD is congruent to BC. Prove that EH times CH equals FH times AH. So let's unpack what they give us first and mark it up on our parallelogram, our quadrilateral. So we have EF is parallel to AD. So here's EF, and it's parallel to AD over here. EF is also parallel to BC. So EF is parallel to BC also. So all three of these are parallel. And we also are given that AD is congruent to BC. Now we need to prove this equation over here. So when we see this, we know that we're going to have to prove these two triangles, triangle AEH, these two inside triangles AEH, and triangle FHC, similar by angle. So the goal, so our little goal, so here we have to prove this, but to get there we're going to have to prove that triangle AEH is similar to triangle FHC by angle. So once we prove that, the reason this is our goal, once we prove that, we know that the corresponding sides of similar triangles are in proportion, and if we could set up a proportion, we can show that these sides EH, CH, FH, and AH are all in proportion to each other. So that's why we're focusing on these two triangles, because this is what we need to prove. So of course we're going to have to start with our statements and reasonings. So for the first part, for number one, you're always going to want to list everything they give us. So everything up here we're just going to put for number one. And here we're just going to put given for the reasoning. So part two. So what else can we mark up on these two triangles if this is what we're focusing on? Notice they have vertical angles here, which we can say are congruent. So angle EHA is congruent to angle FHC. And this is based on vertical angles. So looking at this, we know that AD is parallel to EF and is parallel to BC, but it didn't explicitly say that AD parallel to BC. So let's just write that here officially. And we're going to write this in order to prove that this quadrilateral ABCD is a parallelogram, which will help us find more information to put these triangles are similar. Up next, we're now looking for our next angle, and to do that, we're going to prove that this is a parallelogram. So we have AD is parallel to BC, and we know that because this is just the transitive property of parallel lines. So if this and these are parallel, and this is parallel, then obviously this and this is going to be parallel too. So just a little logic there. So number four, now we can state that ABCD is a parallelogram. And the reasoning for this is that a quadrilateral with a pair of sides, both parallel and congruent, is a parallelogram. So here we have AD is congruent and parallel to BC, therefore we know this is a parallelogram. Okay, next on our list, we can conclude, because we know this is a parallelogram, we can conclude that AB is parallel to DC. Because this is a parallelogram, and opposite sides are parallel. Okay, so now here's where our other angle is going to come in. Now that we proved that these opposite sides are parallel, we can find our other angle using the alternate interior angles that are formed when there's two parallel lines cut by a transversal. So here are two parallel lines, AB and DC, which we just stated. And now notice that AC cuts it, so we know that this forms those angle relationships. And we get an opposite interior angles, alternate interior angles, where angle EAH is congruent to angle FCH. And the reasoning for this is alternate interior angles formed by a transversal and parallel lines. So now we can prove these two triangles similar by angle. So triangle AEH in here is similar to triangle FHC in here. And this is by angle. And now, because they are similar to each other, we can write a proportion. So we can say that line EH over FH is equal to AH over CH. I'm just going to highlight the different colors of each side here so it's easier to just see. So we have EH over here corresponding with FH over here. And then AH going this way corresponding with this line here, CH, in the other triangle. Okay, so now the reasoning for that is that corresponding sides of similar triangle are always in proportion to each other. Okay, we're almost done. Now we can finally state what they wanted us to prove. And you can see that we just cross multiplied here. So we have EH times CH is equal to FH times AH. And the reasoning for this is that the product of the means equals product of extremes. And that's our answer. So this is the last question of our test, so I wish you good luck with the Regents. I have a lot of practice questions that go over more examples, different topics throughout this test, so please check those out. Good luck and happy calculating. So if you're looking for more on this test, check out the playlist in the link below. And thanks for stopping by. Happy calculating. Need more practice? Check out MathSux.org for more questions. Link below. Also, don't forget to subscribe. Happy calculating!